Welcome to section 12.1 on 3D coordinate systems. This is our very first topic in multivariable, and as you'll see over the next couple chapters, our real goal here is to develop the basic tools we need to find anything in three-dimensional space, how to talk about things, where are they going, how are they moving. So this kind of gets us to our initial question of how do we find things? How do we locate anything? Well, we need two things in order to find anything, really. We need to know where we are, or some fixed reference point, and we also need some kind of coordinate system, and you'll see this mirrored in physics as well. We need some kind of coordinate system. Now, our traditional coordinate system that we've been using, and you've gone through some calculus, you've seen a couple different kinds of coordinate systems in your day. Some of the basic coordinate systems you've probably seen. Let's see if this one's primed yet. Oh, no, that one's not primed yet. Some of the basic coordinate systems you've probably seen so far are like Cartesian. Cartesian's the classic one, and the one we'll be talking about today. So 2D Cartesian coordinates, right? You're familiar with them. You've got your x and your y. We do have a reference point, the origin, which is, of course, conveniently located at 0, 0, defined to be 0, 0. And if we want to locate some point, AB, right, up here, A, comma, B, well, we know how to find that point. We definitely know how to find that point. All we do is we come over some distance A, and we go up some distance B from the origin. And how do we know we go over then up? Well, we know that because that's what Cartesian tells us, that in our ordered pairs, x always comes first. And we've got some other things that you might recall. We've got our ordering of the different quadrants, right? We've got quadrant 1, 2, 3, 4, etc. Well, in 3D, we need an x, a y, and a z. And what's kind of fun is that we draw this in a way you might not expect. The way we draw it is like this. We do draw our three axes, and I'm not the world's best artist, but that's okay. You don't have to be the world's best artist to do this. So here we've got our 3D coordinate system, and what might be a little strange to you is that this one is x, this one is y, and this one coming up here is z. So you'll have to get used to drawing these coordinate systems by hand. Once again, we have an origin right here, and this is defined now to be 0, 0, 0. And let's say we want to locate some point A, B, C. Well, what we're going to find is that that's some point where what we've done is we have come out some distance A along the x-axis. We have come out some distance B parallel to the y-axis, and then we have gone up some distance C parallel to the z-axis. And now this gets a little bit tricky to plot sometimes. So as an example, let's choose let's choose the point 3. We're going to try to plot this point 3, -2, 5. Now 3, -2, 5. What we do is, well, I can come out 3 ticks on this axis, right? So I can come out just arbitrarily. We'll call this 1, 2, 3. Now to go negative y direction, this is the positive y direction, so I got to go back this way. So I'm going to just quickly extend the y-axis real quick and give myself a couple tick marks. So let's call this +1, -1, -2. Now what's a little interesting is I got to kind of draw a little parallelogram, do a little perspective drawing. So there's +3 in the x direction, -2 in the y direction, and now I need to go up 5. 1, 2, 3, 4, 5, up into my previous writing here. Again, perfect planning makes perfect. And what's kind of interesting here now is I've got to sort of figure out draw the other parts of my parallelogram, and conveniently, the point that I've decided to plot is right here in the middle of what I had written before. There it is, there's 3, -2, 5, right where I put it. So again, we came out 3 in the x direction, back 2 in the y direction, and up 5 in the z direction. You might notice that this seems a little ambiguous, that there might be other points that I could plot that would kind of line up, that if I point, 1, 1, 1, and, I could think of other points that might be similar to that, right? And if you're worried about that, you're absolutely right. Drawing things in 3D is very tricky, and that's what we're going to start with early in this unit, is drawing things accurately in 3 dimensions. So just real quick before we do a worked example, I want to talk about a couple other pieces of vocabulary we'll get. So I'm just going to redraw my coordinate system here with my x and my y and my z. So we do in fact have a couple familiar places. We do have an x-axis, as you might recall. So here's our x-axis. That's still called our x-axis, and our y-axis. And down here, this whole thing down here, if you like, this is called our xy plane. We'll talk a lot about the xy plane. That's where you've been doing a lot of stuff in math so far. And the xy plane just happens to be the plane where z equals 0. Over here on the left side, we've got instead where y is equal to 0, what you might think of as our xz plane. And for those of you who have done any CAD, this will be familiar to you. And last but not least, over here, we've got our yz plane, defined as the part where x is equal to 0. This region that we usually draw here, positive x, positive y, positive z, is in fact called, this is a very grandiose name, the first octant. The first octant, just like the first quadrant. And why is it an octant? Because now there's 8 instead of 4. Don't ask me which one is the second octant, or the third octant, or the fourth octant. I don't know. I just know that the first octant is where they're all positive. And we'll mostly be playing around in the first octant. All right, so that's about covers it actually for 3D coordinate systems, at least Cartesian. We'll see 2 other coordinate systems later in the year. Spherical and cylindrical coordinates. But we're going to stick with Cartesian for a little while. All right, welcome to the 12.1 worked example. So we just learned about 3D coordinate systems, or at least about Cartesian coordinates. So let's try something with it. And we're going to kind of start this exploration with a pretty simple, innocuous little function. Let's plot y equals 2. You've seen y equals 2 before. Your good old friend. So you know how to plot y equals 2, and let's actually just start with Cartesian coordinates, 2D Cartesian coordinates at least. So here we go, 1, 2. Now if I was graphing this, right, remember y equals 2 is not just one point. It's lots of different points, and you probably just, without even thinking, draw this line. Y equals 2, there it is. Why is that the line y equals 2? Why is it all stretched out? Why is it a whole line? Y equals 2 is like, why can't I just pick this point, 0, 2? Hey, y equals 2 right there. Or this point, 5, 2 for say. Why is it the whole line? Well, one way that I like to think of this is that x is free. You could also say like x doesn't matter, or x isn't in the equation. X is not constrained. So you get to kind of spread it all out in the x direction. And that's going to be a useful idea as we go into thinking about 3D. So let's draw ourselves some axes here. So here, once again, we have x and y and z coming up. So let's bring ourselves out once again 2 in the y direction and draw our line. Now I have to be a little careful, draw it in some perspective here because, I want to be... All right, there's my line, y equals 2. And, similarly, hey, look, here's the point 0, 2, 0. Here's maybe the point 5, 2, 0. We've just kind of transferred the line over. But what about this point? What about this point? 0, 2, 5. Hey, y is also equal to 2. Or another point down here, right? I could come really anywhere else where y is equal to 2 and get the same value. I could come over here to, 525. And y is still equal to 2. So what we start to realize is that this is not a line anymore. Y equals 2 when we expand into 3D. Z also doesn't matter. So we get to come up, and what we actually get is a sheet. Y equals 2 is not a line. Here it was a line. In 2D, it's a line. In 3D, it's a plane. It's a line. It's a plane. It is a whole sheet. In fact, I've only drawn a little square of it, but it's worth remembering that this sheet actually extends infinitely in every single direction, well, every flat direction. It's parallel to the XZ plane. It's parallel to the XZ plane where y equals 0, and kind of just, it's an infinite sheet that slices across our 3D coordinate system. And it is truly infinite, which causes a couple problems. And I'm going to illustrate one of those problems by attempting to sketch a slightly different plane, which let's try to sketch the plane x equals 1. No, let's get crazy. Not x equals 1. Let's sketch the plane x equals 4. Yeah, there we go. Again, you might start with this little line. It's not bad to start with a line. But let's say I really wanted to capture the infinite nature of this plane. Well, I might start to draw, to sketch it out, well, as broad as I could and as tall as I could. And you got to be a little careful. Because it's an infinite sheet, and it's right at the foreground of our picture, you could imagine sketching out something that covers your entire field of view. And you end up with just a scribble, which is kind of what it would look like. You'd just be facing an infinite wall. That's not useful. So how can we draw it so that it actually tells us something? Well, we could cut a little section of it that's going to capture the behavior of the holes. Now, often we'll capture just the section in the first octant, but we don't necessarily have to do that. I'm just going to do it here. And we can just draw a small sheet of it. And that gives us the impression of what x equals 4 looks like without actually requiring us to, spend an infinite amount of time drawing an infinitely large sheet. And this is where we're going to get to one of the most important skills in the class, especially in the beginning of this class, which is sketching. Now again, I will tell you consistently, I am not the world's greatest artist, and you don't have to be either. Some of you probably are. But sketching is really important. Why is sketching really important? For one, it makes you think. You have to really think about what this thing looks like. You have to think about what parts you have to draw, what parts you don't want to draw. It also helps you build intuition. Especially as we move deeper into the year, it's going to be really helpful for you to be able to hold in your head the idea of, oh, this is what a plane looks like, or a paraboloid looks like, or an ellipsoid, or whatever we might have. It's really helpful to kind of move these things around in your mind, and drawing it, moving your hand, is the most important first step to that. All right, these are two relatively simple examples, just sketching some planes. We're going to see some more complicated examples in class, drawing other things. But I want to leave you with this little teaser question, which we'll come up with in class, which is, what do you think x squared plus y squared equals 1 looks like?